Thank you, Audrey, and also thank you everyone here that joined this session today. I'm Daniel Kasempur from the working group of Professor Per Kröger from Kiel, northern Germany. And this is now the second time that I have the opportunity to give you some input or some also experiences on managing and processing scientific data, let it be small data or even in larger scales. And a question that may arise here is, what can one expect here? Well, some sort of like big picture, like more in the width and less in the depth. So what you can get here is, what do we have currently? What are the different flavors, the different, how to say, archetypes of storing, managing data, and having it ready for the data analysis part, or for designing our own algorithms and methods to mine data for patterns, for example. And if you have questions during the presentation, feel free to raise hand. I hope that I see it. If not, please unmute yourself quickly and speak up. And if you're interested in more details, feel free to get a Zoom call or some meeting with either Professor Kröger, so PKR, you see here the email address down there, or mine would be DKA at informatik.university-kiel.de. And well, I assume all of you that are here got some connections with data in the most diverse way, and this is how to say, some sort of a classic that we have, the so-called KDD process that you see here from Fayad et al. It's quite old from computer science perspective, from 1996. However, it describes the journey from the originally raw data that we have, data that we obtained by whatever means, and from different sources of different types, up to the very end. What we hope to get out of this data is knowledge. And sometimes one may say, well, if we have data, then we already have knowledge. So what's the problem? And the probably most prominent example that we have is the Human Genome Project. It was at the beginning of the millennia quite famous. And well, what happened there is basically we got the human genome deciphered, or most of it, and people thought, okay, now we have it. And some media, it was also called God's plan unrevealed and whatnot. However, having the genome information is one thing, or the data. Processing it, mining for patterns in it, discovering relations in it, that is a totally different story that we are looking at. And this KD process, some of you probably it's already known, but just as a brief recap here, we have our data from different sources, from different repositories. We perform some data cleansing and some data integration. So which data are we going to use, and is there some noise? Are there some missing values, and so on and so forth? Then we store the data in something like a data warehouse, for example. On this cleaned and integrated or fused data from different sources, we apply then some transformation, some selection or projection. So which features are relevant, which samples are relevant, and why are they relevant? And what we have then is a subset of our original data that we see here. And this is our task relevant data. This is the data we're going to work with. And on this data, we work on it by performing data mining. And data mining encompasses different types of methods. Let it be statistical analysis like mean, variance, median, etc. So foundational statistics, up to deep learning methods. And the goal of this whole data mining, that comprises machine learning, and it comprises statistics and so on, is in the end, or not in a pre-last step, to discover patterns. And patterns is a quite vague word, or something that's, one can say, yeah, everything is a pattern. Or what do we mean it by in this context? Patterns in the sense of discovering data that you collected and pre-processed, discover within this data relationships between objects, between instances that you measured, or relationships between features that you measured, like between dimensions, between, let's say, blood pressure, the relationship between blood pressure and how to say, and how often I do sports a day, or how many hours. So to discover relationships in forms of correlations, or in ideal case, even causalities, causal relations. And after having these patterns discovered, we get to visualization and evaluation, because sometimes we may discover patterns. This happened indeed to me, like when during my PhD, I worked together with ornithologists, so the bird people, and I was like, look, we found here really nice clusters, groups within the data. This is also a pattern. And the domain scientist, she looked at it, nodded, and said, looks interesting, but it's meaningless. It doesn't tell you anything that is meaningful, where you say, aha, that makes sense. So having patterns is one thing, but there's still the need to evaluate it, mostly by a domain expert, to see if the patterns are really meaningful, if they make sense, or if they do not make sense, to pursue the question of what happened there. Is that some artifact, or is that something really exciting new? And this is then the knowledge at the end. And sometimes we also have a feedback loop that we go back and forth here. And what we actually have at this point is, before we can do the magic stuff, like the data mining up to knowledge, before this can happen, we need to manage the data. So that's something that, how to say, cannot be escaped with, or just rarely. I mean, there are certain occasions and also collaborations that we have with different domains, like mechanic engineering and such, where we recognize, oh, there the domain scientists already cleaned the data because they already knew what is noise, what is not noise. But there are also cases where this does not exist, and one has to look into it more detailed. So what we are looking in this lecture is like up to here, up to the task relevant data, this part. And there may be also lectures that get you through this second half, so to say. And one thing that we had is actually the term big data, especially something like 8 years ago, 10 years ago, was extremely hyped. And it is, one has difficulties to express it in other terms than to say it is a buzzword that we had. And it has been like triggered by McKinsey in 2011, mostly from highly focused from a business perspective at this part, and also a technical perspective later on. And if we look today, yes, this business thing makes sense, because we kind of like pay with data. Whenever we're using Facebook or the Google search engine, or Twitter now, X, or Amazon or whatnot, we use service, but at the same time, in exchange for providing data. And this data that we exchange for the service that we use is actually further utilized by the companies to improve their target advertisement. Like, I mean, you know it from Amazon. If you buy something there, they say people who bought this also bought that. And what factually happens is a profile is learned or is gained over time from your consumer behavior. So in fact, data is sold. Although there are now some endeavors, I think recently Facebook or Meta said, hey, you can have a paid account and then we won't sell your data or something like this. Well, and over the past decade almost, several terms have emerged or have been rediscovered, have been used synonymously, even in extreme case. We have data science and artificial intelligence, or business intelligence and data mining, and machine learning, or industry 4.0. So you see, it's just buzzword bingo at that point. So let's put all this buzzword stuff, buzzword bingo aside, and get to something that has, like, how to say, more substance, or is something that persisted even the hype phase of big data. And this is related to the question of what is big data, which strongly depends to what we have as a use case or what we're looking at. And quite prominent is the so-called 4V. Originally, it was 3V out of these 4. Then there were some papers afterwards in 2015 and 17. They said it's 6 Vs and 7 Vs. And the 7th wasn't actually a letter starting with V, but with something else, with R. And however, these 4 are those that persisted time. And what are these 4 Vs? So big data is characterized by these 4, how to say, properties. First one is by volume. So you may have data from different sources, like volume on the disk, on several different disks, and high number or different number of instances, meaning rows in a table, or in the sense of columns, like features or dimensions. And then we have velocity, where the assumption behind it is that you have data that is changing over time, like new data is arriving at a potentially very high frequency. And this data is from a sensor, for instance, that we have. So a sensor constantly yields you data like the carbon dioxide level or the temperature or the pH or salinity or whatever we have, like sea salinity or whatnot. So this is data that we keep collecting at a high velocity. And then we have variety. Not all data is the same. You have data from different types, and I bet you know quite a lot of different types of data. Like they can have structures that go beyond some simple table, like vectors, sequences, graphs that we have, tensors. So you can have also a special type from graphs like trees, a hierarchical structure, and so on and so forth. So you don't have necessarily data only in one type. You can have it in terms of video, it's a sequence of images. You can have it as some connection graph, like the relationship graph on LinkedIn or Facebook or what we have, and so on and so forth. So different sources rely on different formats representing different types of data. And we have as the last V here, the so-called veracity, and this implies a certain uncertainty in your data. So the data that you have may be noisy, may be manipulated, may be misinterpreted, or even like completely faulty to a certain degree. And therefore, we have to consider data objects as samples, not as facts. So one has to be careful when you have highly noisy data, because if you take this data to learn something or to discover patterns, these patterns may heavily be biased or skewed by the uncertainty, by the noise, for instance. And there is something that, how to say, it's difficult to follow, like velocity. Yeah, I mean, I have my sensors and I have a few kilobyte or megabyte of data. What could be the worst happening there? Well, one example that I'd like to share with you. For this, I will go to the browser. And here we have this one. So here, just a few use cases. Number one, imagine you're leading a new data analytics division at CERN, so where the Large Hadron Collider is located, for instance, and you are being told that on average per day, 1 petabyte, this is 1 million gigabytes of data are generated. Wow. And during one LHC run, so a collection of different experiments, around 600 petabytes, meaning like 600 million of gigabytes of data are collected. And this is because okay, it sounds like a big number. What's the relation? That's around 20,000 years of 24/7 high definition video recording. Well, let's see. I doubt that Netflix can top that. And one question that we asked also in our lectures, what are the challenges that one faces here? So you need data management of a lot of data. This data may be noisy. This data comes at fast speed and needs to be recorded. And one anecdote, since we once were at the CERN, at the Large Hadron Collider, was they collect the data on their hard drives, and they pop out the hard drives, put them into a truck, and drive with this truck to their destination to put them in, archive there, and to take like samples, like take single hard drives and read in the data. Because with such amounts of data, such high volume of data, sending it through even a fiber optic pipeline wouldn't take still quite a lot of time that we have. And another second use case is like, imagine you have been acquired after working at CERN by the Deutsche Bahn, so the German train agency or train company, and in the analytics division. And these are actual real use cases that you see here. And your team here is dedicated with the analysis of delays in the schedule. And for those of you who do not know it, the German Bahn's infrastructure, there are quite some, how to say, delays when taking a train. So there's a high probability that you are taking a train and it gets delayed by a certain factor. And first, you're being told that there are 4 major categories that contribute to these delays, like the infrastructure, the rails, the signals, the electricity power supply, and so on, or the state of the vehicle. The vehicle may have a malfunction, or environmental effects like weather, ice, strong wind, rain, and so on, and also the human factor, so the travelers, how they arrive from a delayed train uniformly in batches whatsoever. And the current objective by the management of this scenario is to be able to predict in real time here if a single train is going to be delayed based on features from these 4 categories. So here we have, as an example for us, challenges that we are facing, like a lot of data from different sources. So we have the volume factor. We have data arriving at fast speed. So we have a lot of data from different sources that are coming through, like the logs or the information on the rail state, how the rails are, if their signals are malfunctioning or not, and if previous trains got delayed or not, and so on and so forth. And we have variety. We have like different types of data, and to a certain degree also veracity. So this data may have some error to it, or the one log of data that we have may not be up to date and is actually telling you there is a delay of 10 minutes, but actually it was 20 minutes that was delayed, and so on and so forth. So this is one concrete use case where you have all 4 V's kind of like involved into this whole pipeline. And to get back to the slides here, we continue. Yeah, I can see that. I have to handle a bit. Yeah, there we go. So there's also a picture that Professor Kröger likes quite a lot. We have these also, to a certain degree, we have examples for volume, like 6 billion of people and have cell phones. That creates a lot of data, like a lot of 40 zettabytes of data. And like most companies in the US have at least 100 terabytes of data stored. And in velocity, we have like cars that have close to 100 sensors, or 1 terabyte of trade information. So high frequency trading, there you have velocity in it. And 18.9 billion network connections that we have from 2016. So already also quite got some time. And you see, so there's not an academic ivory tower thing, these 4 V's, but something that can actually take place. And I'm curious or excited to hear from you after this talk, if you have faced situations where you were challenged by volume, you were challenged by velocity, by a variety of veracity. However, we may have in the beginning a bunch of data, I mean really a lot of data, but this amount of data can get shrinked. It can melt actually to a smaller size. So in the beginning, we have our raw data, and it's big to a certain degree, fair enough, but during the data science process, as we had several slides ago from Fired et al., the data melts down. It gets smaller and smaller and smaller. So data shrinks. And As the last step for complex tasks like the high quality, the gold data that we need can be small. So there may be cases where we have not enough labels or noise or irrelevant information, irrelevant features, or actually a too high resolution, too low actually. So the consequence is that we may have in the beginning a lot of data, but in the end, it all still fits in our main memory, in our RAM. And we let our Python or R scripts and visualization tools run over that. And big data systems, they often support the first step in the process to kind of like get from huge amounts down to the smaller amounts, from raw data to the pre-processed data, and from pre-processed to usable. But before we get to any of these big data frameworks or big data tools, we first dedicate our attention to the classic database management system that we have. And just a brief history, like in the early 60s, IBM had developed some hierarchical database model. You could think of it like a tree-like structure, and the data was stored as records that were connected by links. And friendly remark, just forget about it. And here's a side note. This is just in case if your grumpy grandpa is telling stories, you see this favorite scene from The Simpsons, old man, yeah, it's at cloud. But around about 20 years later, we had this rise of this advent of relational database models, where the novum was that data is stored in a collection of tables. So you have several tables, and these tables are composed of rows and columns. It follows a strict relational schema, so-called first normal form. We shall get to it later on. And SQL became the standard language, being based on relational algebra. And I'm not sure how many of you here in this round have ever heard or got contact with functional languages like Haskell or Lisp, for instance. These languages are also founded on some mathematical framework, namely the lambda calculus. And that gives actually a quite strong backup on what they have there. So when it comes to prove something that this program can do something, then this mathematical underpinning augments it or supports it quite a lot. And the same here. So we have the SQL language, or standardized language, and this is founded on the relational algebra concept. And so relational database management systems, they became and still are, like, how to say, the standard for managing at least corporate data. And I'm also curious who of you in this round is using relational database systems, database management systems, since I know from my time, my origin in my bachelor time, undergrad times was in bioinformatics, they actually referred to Excel sheets and CSV files. So the use of databases was not that common. And while there are certainly cases where you don't need a relational database management system, there we had cases where one should have used them. And we shall come what are the benefits and then in which sense one should rely on, or under which conditions one should rely on them. So we say one aspect that we have regarding the properties of relational database management systems is that they have been designed for transaction data, and again motivated by daily business of companies like financial transactions, booking of flights, or order transactions, and so on and so forth. And for that, they have three important aspects that they support. Number one is data consistency, availability, and fault tolerance. So these are the demands that the database or storage system should provide, and which relational database management systems do provide. Then short read-write operations on the data. You don't want to wait several minutes or hours for a simple query. And we have here the scale. So the scale for which relational database management systems are constructed is in a range of several megabytes of data up to gigabytes of data. When it comes to several terabytes of data or beyond peta or exabytes, then we get to something else like NoSQL or distributed systems. which we get later too. And the advantages that we have here from these relational database systems is we have data independence, which improves flexibility over file systems. Now one may ask, okay, what is data independence? What can we think of it? Well, if you have a specific tool, like you write your own software that reads and writes the data, and you have your own file format and whatnot, then it may be operating system dependent, it may be CPU architecture dependent, and you have to, if you want to add a certain column in your software, self-homebrew software that just writes the data down, then you have to change your software. And these relational database management systems, they abstract that away. So we as users of these database systems, we create tables, we create relations, we fill it with stuff, but we do not have to take care of what is the underlying operating system, what is the CPU architecture, and so on. That is something that's just abstracted away and none of our business unless we are really interested into certain aspects. And it has a sophisticated transactional concept like this so-called asset properties, which I get later on to. We have synchronization of multiple users. We have backup and recovery strategies. We have an automatic and to a certain degree transparent and understandable or comprehensive or explainable query optimization, and so on and so forth. So there are certain aspects that speak for using relational database management systems. And just as a quick intro, like relational models relies on tables, like everything is stored in tables as the one and only way to structure the data in this realm. And a table represents objects with a given set of features, and every row in this relations in these tables represents an object, which in some literature, now you have some series of synonyms, and a row is the object, is also in some literature. Entry is a tuple or is the instance. Well, and the columns, on the contrary, they are the so-called attributes in these tables, or features, or variables in statistics, or dimensions. So columns have like atomic data types. So they are of fixed length in terms of bits, for instance. And the keys are identifiers for rows. What these identifiers are, we shall see in the next slide. And these complex relationships between objects, they are modeled by references between corresponding tables to so-called foreign keys. And here you see also again the anatomy, so to speak, of the relational model here, with the concrete values of the attributes that we have. And this top line here, actually this header, is also denoted as a schema, where you have the name of the columns and its data type, or the domain to which it belongs. However, since we mentioned keys, what are these keys? Well, each row that we have in our relational table must be uniquely identifiable. This is a bit contrary to what we have in programming languages. For instance, in object-oriented languages, objects are identified by identifiers or by references. In the relational realm, rows are identified by concrete attribute values that we have. And one or more attributes, they must be also, one or two columns must be flagged as keys. Something that we can use as a key has to satisfy certain conditions. So the values of these columns, of these attributes, they must be unique, no duplicates in this sense. And keys identify rows uniquely, and keys can be used to refer to point to unique rows from other tables. A concrete example, we have here employee table and we have here division table, and we say here in this column division, this 01 of this employee table refers to the division number column of the division table, so that if we have here Erwin Huber, then we can look up here through this relation, through this edge, division 01 is the bookkeeping region, bookkeeping division. Then there is something called normalization, and there's a lot of theory behind it and different types of normalization, but let's keep things simple or as intuitive as possible. And for that purpose, let us take a look at this relation at this table called lectures, and we have these attributes, these columns, lecture number, title, and term. And lecture number and term are the key attributes. So here, these two columns are together a composed key. We require both columns to have something unique. Now, what is the issue that we're going to face with this? Well, we need to store the title of a lecture, if you see here, several times. We have here 013, Machine Learning, Winter 2017, 013, Machine Learning, Winter 2018, and there could be arbitrary more. So for any two rows, R1 and R2, it holds if the values of R1 and R2, like this one and this one here below, in lecture number, what we have here, are the same, the value of title in R1 and R2 must be identical too. So if you have a lecture with number 13 and the next one, next entry, the next tuple or object is also the lecture number 13, then we can assume here that the title of the lecture must be the same. In both cases here, machine learning. So this is what we call here a functional dependency. Here the title that we have depends on the lecture number. Now, consider the following case. So we want to change the name from the lecture from machine learning to introduction to machine learning due to some accreditation or some other reasons. We just want to change the name of it. And under the current case, we would require to change this name multiple times in this whole table. So we'd go down, and wherever we have an entry called machine learning with the lecture number 13, we would need to change it to introduction to machine learning. And if we are not aware of it, that this title is actually redundant, we might miss some tuples, can happen, so that this one is by accident not renamed to the new number. And by missing this, we may get inconsistent data. So having some redundancy is a waste of storage. I may say, well, obvious, nothing new to us. However, the real issue we are facing here is that this may cause anomalies like an insert anomaly as we have here, because you insert then the new name or edit to a new name, but some of them you forget, and then you have once an entry 13 machine learning and once an entry 13 introduction to ML. So you have an inconsistency here. And how can we get out of this? Well, we perform normalization. And in normalization, by definition of the keys, an entire row of a relation is always functionally dependent on the key. And these functional dependencies are welcome and do not cause redundancy. However, there may be more functional dependencies where an attribute may be functional dependent on only a part of the key, not on both columns. Like, for instance, title depends on lecture number, and this is called a partial functional dependency. So in our previous case, title was not dependent on, if we flip back, on the term, that is independent of the term, but it's dependent on the lecture number, so only on a part of the composed key that we have. And an attribute may be functionally dependent on an attribute that is not actually a part of the key. This is what we are going to call a transitive functional dependencies. And normalization helps us or provides a remedy to this by getting rid of these functional dependencies that are not related to these properties that we have of the keys, because they can actually cause anomalies due to these redundancies that we have. So in theory, there may be more functional dependencies to take care of, but in practice, only the aforementioned functional dependencies are like erased. So, and in our concrete example that we had, how can we, how does it look like when we apply a normalization? Well, in this particular case, we can solve this issue by splitting the table that we originally had, which obviously suffered from a partial functional dependency, into two separate relations, namely one relation lectures, where we have lecture number and title, and one relation that should be named somehow different, like current modules, for instance. And so this is an error. And here we would have then the following case, we would have lecture number and term. Now you may ask, okay, but what is gained in this particular case? We got now two tables, so what's the benefit here? Well, if we change now the name from machine learning to introduction to a machine learning, then we change it once and only once, and this is here. And all the other lecture number 13s, we would look up here in lectures and see, oh, it's now called Introduction to Machine Learning. So by splitting it into two separate relations, we got hereby this functional dependency resolved. And schemas, they do not have any functional dependencies of attributes on part of any key candidate and any functional dependencies of attributes on non-key candidate attributes. They are called the third normal form. So if these two conditions are satisfied, then the relations that we have, they are in the so-called 3NF in the third normal form, because they meet the formally defined set of normal forms that are 3 in this case. And some words or like almost closing words on SQL. At that part, the structured query language is a programming language of relational database management system. Its API is like super mature. We have to define data structures that are our schemas. We have to store and manage data in terms of an insertion or a deletion. We have the means to manipulate and to query the data. And well, to be good in SQL, you need approximately, how to say, well, this is some rule of thumb, 2 weeks and some continuous practice to work with. However, as often your mileage may vary in this sense. And another aspect that we had in the very beginning of this part is the transaction concept in the relational database management system. And the key that we have behind this is to synchronize multiple users and the availability that we have in case of some errors or crashes through this transactional concept that is provided. And typically a user interaction, so a program or a session, can be regarded as a transaction. And a transaction, to have some intuition, you can think of it as a sequence of read or write operations that preserve a consistent database state. So what is imperative is that you start from a consistent database state, you do your sequence of operations, read and write, and in the end, you arrive again in a consistent database state. And the transaction management of a DBMS has two main tasks, main objectives, like you had two jobs to do. One of them is synchronization. So you have the coordination of several users, because if you change something from user A to user B, you want that it's not only this change visible in user A, but also in user B over there. And you have a recovery, so solution to crashes and other issues that may arise. For transaction console, we have an example. You are at a bank and you have a transfer of 200 euros from the account of Huber to the account of Muller. So Huber is like subtracting 200 euros and these 200 euros are added up to Muller. And what happens here is like you first decrease here the balance of Huber by 200, minus 200, and increase as the next operation the balance of Muller up here by 200 euro. What happens, however, is that we get a system crash. And what you want here is that you do not end up in a state of Muller having 200 euros subtracted, but Huber having 200 euros subtracted, but Muller not having received anything. So here we have an inconsistent state. And this is something that the transaction system of relational database management systems take care of, that you do not end into this inconsistent step. You may probably ask what happens, but what are you going to do now? Because you can't retrieve and say, oh, I forgot now after the system crash, I have to add up 200 euro to Muller. No, what happens is you have a rollback. You get back to the last good state, and then execute it again after this crash has been resolved. And there's some airport issue or use case. So the flight operations prints out the names of passengers and the number of passengers on the flight, Lufthansa flight, and the check-in checks another passenger, one of these late arriving honor or whatever status they have, senator status. So here, actually, Per, not me, is jealous because of their status. And one possible schedule is like the flight operations prints out the list of names. Okay, you have 10 names on it. The check-in checks the passenger phantom mime in afterwards, after we have this list of names. And then the flight operations again prints out the number of passengers. And you say, okay, it's quite obvious, or quite not obvious, but fine. What happened here? Well, what went wrong is that the flight operations get inconsistent information because phantomime, the passenger phantomime, is not on the list, but is counted to it. So the check-in will say, oh, we don't have, the flight operation says we don't have that person on the list because this is the last consistent list that flight operations had, but they count more people, namely the number of names in the original list under step 1 plus the phantomime. And this is some inconsistency. So the flight operations may say, 10 names, but I see here 11. What happened? And one, how to say, fundamental thing that is behind this relational database management system is the so-called ACID principle in context of transactions. And this defines some set of properties for transactions that a typo should be guaranteed by a database management system. One of them is, in this ACID principle, is atomicity. So a transaction either runs completely through, or it does not complete, so does not have an effect at all. So it's either complete or nothing happens. It rolls back. Then we have consistency. A transaction preserves any integrity constraints, like integrity with respect to some file types or with some default values and so on and so forth. Then we have isolation, even though transactions, they are executed in concurrent and parallel. We have the situation that for the effect of each transaction must be the same as if they have been operated serially without any concurrency. So you want to have them kind of like isolated and independent, the single transactions, not that one influences the other one. And you have lastly durability, so the effect of a transaction that successfully completes, so like gets to a commit from the system, if in terms of Git, it must remain in the database, even in the case of a later crash. So if you did something, you did your transactions, everything went fine, then it must keep there, it must remain there, even if now something is broken. So these are the 4 aspects that should be maintained. And we shall see in context of NoSQL in the non-relational realm, this asset does not necessarily hold under all conditions or has to be given up to a certain degree. So to wrap it up for this relational part, they are, how to say, de facto standard in data management, and they offer some mature and powerful means or tool set that we have here, technology for managing like corporate data. Data is modeled in tables, just like Excel tables, but well, Excel tables got their own story. I'm not sure if you ever stumbled upon it, but there were some cases where some computational biologists recognized, oops, Excel did something under the hood, changed it from the date back to something, and the values that they had, well, they were not consistent, not what they originally recorded. So also another reason to rely in this case either on plain CSV files or to put your data in a database. And we consider normalization for non-redundant anomaly-free storage. This is also a strength. ACID is the holy grail that should be maintained in relational database management systems to have like security, consistency, availability of the data assured, even if we have parallel access with multiple users. And SQL itself as a query language is a powerful standard API for data management. So far, from data management, motivation over to relational database management systems, and now we proceed to managing like spatial or geodata. So specific realm, so to say. So what is so special about geo objects? They have spatial coordinates, usually 2-dimensional, also 3-dimensional if we have, for instance, the altitude included. They may have a temporal dimension. So we have an object that changes its spatial coordinates, its location over time. It happens. We had in a collaboration with ornithologists in 2018, where we had the on some curfew birds, actually the ornithologists did that, that's their expertise, their realm. They put small sensors on the back of the curfew birds, and the research question was, do these birds exhibit some sort of swarm behavior? Because they are predominantly known to be like lonely flyers. They just fly on their own and get somewhere. They're not exhibiting any swarm behavior. And the question was, are they really entirely single or solo birds, or are they also temporarily even putting them together? And what we had there was also, we had 3D coordinates, longitude, latitude, altitude, and we had like the heartbeat of the bird, we had the body temperature of the bird, and we have recordings on an hourly resolution. So every hour, where is the bird now? No, or it was hourly, and later on they had it even on 10-minute intervals, a higher resolution, temporal resolution. So you see, it was not only longitude, latitude, altitude, and time over time, but also like heart rate and the body temperature and so on and so forth. So have additional non-spatial attributes. And the types of attributes that we have, so they are spatial, like coordinates of a point, area of a polygon, or they're topological, like a polygon 1, like a square and a triangle. As polygon 2, they are neighbors, as we see here on the right-hand side. And they have a common face. So this polygon is here, this particular edge facing this rectangle is facing this triangle, for instance. And they may have some thematic or some semantic behind it, like polygon 1 is actually a cornfield that we have, polygon 2 is a city hall, and so on and so forth. So there are different archetypes of attributes. By the way, speaking of data cleaning and speaking of geo objects, during our work with the ornithologist, we had the case where we said, all right, we want to track the birds, and they have been tracked, and we got the data. And what we did first, we have been plotting their trajectories. So we had, for sake of simplicity, we have here like the longitude and latitude, these two axes, and we had like one bird flying from like Munich, actually, it was somewhere to Tunis. Another bird also from Munich, like something like 20 kilometers away from Tunis, or oops, that's actually more, and so on and so forth. There was, however, one particular bird that we had that was flying here, and that was suspicious. And we're like, what happened? So we took this region, magnified it in the visualization. So data visualization is also something of sometimes can bring so much gain or so much explainability to it that we have here. And we zoomed in, it recognized it was the region of Munich, okay? And the bird was like this. And it kept like doing this and this and this and back and forth. And me as a non-ornithologist, so I'm not from that domain at all, I was like, what happened here? And I went to the domain expert, to scientists, and I asked her, is this bird, is it being hunted by some predatory bird, by some predator, or is it some heart attack, or I don't know, what is it? And then that scientist looked on the data and was nodding and said, that was actually me, because I had the sensor, only the sensor, in the back of my car and have been driving with it through Munich, doing the groceries, getting back to institute, somewhere else, and so on and so forth. Yeah. The lesson that we learned from here? Well, keep your data clean, or clean your data properly, as clean as you can. And number two, talk with your people, talk with the people you're collaborating with. So if there's something besides of this topic of data management, and from the experience that we had with different disciplines, with different domains, keep communicating frequently, asking them, discussing with them, having a coffee with them if possible. That brings so much benefit, because figuring that out took the domain scientist like 4 or 5 minutes. And for me, trying to figure that out, which was actually none of my business, to say, took me like an hour or a half hour to resign and to ask the domain expert. So so far on the well, lessons learned from this particular situation. But we have now here these spatial geodata. There are certain challenges that emerge. One of them is the challenge of the Euclidean space here, for sake of simplicity, in 2D. We have 2D coordinates, point coordinates, and the computers store the real numbers as so-called floating point numbers. So floats with a specific precision, and not all real numbers can be represented as floats. So the problem is the intersection PS of two lines, like L2 here and L1 here, may not actually be representable by a float. And the workaround one may take now, or a shortcut, is to say, hey, we just interpolate to the next float. This, however, what we have here, this interpolation, produces you some inconsistency. So this PS is actually neither a part of L1 nor of L2. It is off the intersection that we have. Solution, or one possible solution, I should say, is by Schneider and Güting in 1994. They stated, so for a given set of points, PR of the Cartesian product of natural numbers over a grid that we have here, that you see, we have a realm, and a realm is a set of points P and non-intersecting line segment S over PR. Well, this is now a bit, how to say, dry. So let's break it down, or to put it in other terms, the intersection of line segments must be on a grid point in PR. So wherever we have here an intersection, since we force our connections on a grid structure as we see it here, this one joint of these two lines must be on a point from this grid. So in other terms, you can think of this so-called realm that we had here above as a planar or a 2D graph, where the nodes are the points, as you see here, and the edges are the line segments. So we have, like, let's say, we have this line segment, and we have here this line segment, and this point that is naturally, in parentheses, given by the grid, that is here our intersection point. And by forcing it to have it to be on such a grid structure, we kind of evade this issue of having an intersection point being off the whole thing. And another aspect is that in this geoinformation systems, spatial data is usually mapped on a relational model. So we keep storing all information in tables again. Here we are. And there are like two prominent flavors of doing this. The one is called spaghetti model, where each object is a sequence or an order of distinct point coordinates. So X and Y coordinates, for example, like some border points, and each object is represented independently. But you can think of it, if you have several objects, like a coordinate 242, 242, 242, you will have some sort of strong redundancy in your tables. And we have a simple model in this spaghetti model with no explicit topological properties. So we have no information if there are any holes in the polygons, if this one polygon is like intersected with the other, overlapping or whatnot. All this information cannot be captured by the spaghetti model. The alternative model that exists is the so-called Tiger model, the topologically integrated geographic encoding and referencing model by Marx in the mid-80s. And here we have a complex, non-redundant or normalized model. So point coordinates are referenced, and we have different data types for points, different data types for line between points, and different data types for surface, like a closed set of lines. And we have a cover, which is actually, a union of surfaces, which we shall see in the next one. The issue that, however, comes also with this Tiger model is we have the issue of normalization. Like there's a high cost to get all information of more complex structures maintained. So the results of a query does not return an object, a particular line, but a set of different rows, a set of different entries that we have. But how does it look like? I mean, it sounds quite abstract on this level. So take a look at this. In the beginning, we have points. So a table of points. And these points, they have an x coordinate, they have a y coordinate, and they have a point ID, just a naming, a key, P1 until P5. What is an edge? An edge that we have here is a connection between 2 points. So we have, and these points here, 11 and 4, point 1, you see here 11 and 4. Then point 2, 34 and 13, you see here, this is point 2, 34 and 13 over here. And an edge is a connection between 2 points. So we have here edge ID, K1 until K6, and we have from P4 to P5. From P4 to P5 down here. So this is our edge K1. And this goes on for all the others. And then we have a third relation, a third table called polygon. And a polygon is actually comprising a set of edges. So if we take this rectangle up here, this rectangle is comprised of the edge K1, K2, K3, and you name it K4. So we have here K1, K2, K3, and K4. They comprise the polygon, this rectangle P1. And K5, K6, and K2, they comprise the triangle, this polygon P2. And polygons, finally, they can subsume something called Parzelle. This is a table of covers, actually. So we have here polygon ID, then how many square meters or the area that we have covered, and an ID for the actual cover here. So you see this has some hierarchical character. So it's a matter of composition. You have x, y coordinates comprise a point. Then 2 points comprise an edge. Then several edges comprise a polygon, and polygons or a particular polygon with information of an area comprises a cover. This is basically one example on the Tiger model. So what we had so far was relational database management system, was some spatial data, okay, but there are still cases where we get to the limits with our relational model. And again, some history, like with the rise of the Web 2.0, the interactive during the mid-millennia, early millennia years, the database management systems, they were put under pressure to scale up. And there are 2 flavors of scaling up. You have the vertical scaling, where you enlarge a single machine, you beef it up with more RAM, with more CPU, with more hard drive space, and so on. But this is limited in space, so you can't arbitrarily beef it up. You also get somewhere by the case of your PC or something, you can't beef it up that much, and it's quite expensive. Typo. And we have on the other side, on the other hand, the horizontal scaling. Here, the principle is that you use many machines and form with these machines clusters or grids that are limited by cluster maintenance. So what happened here in this battle between these two, the horizontal scaling won, and that paved the path for the NoSQL, which means not only SQL movement in the mid 2000s. And the problem is, relational database management systems, they do not scale well horizontally. They scale really well when you are vertically scaling it. So, but if you have several computers, at least at that time, we're speaking during this phase, they did not scale well with it. And the big players like Google or Amazon, they developed their own storage strategies, and systems or frameworks. And we had this NoSQL, not only SQL databases that emerged of different flavors and different type. And today, age of NoSQL, there are several different NoSQL systems. This is even also outdated. It's around 400 different available systems. And indeed, I mean, Google started with commodity hardware from some big storage like Walmart, bought their several computers, linked them together, and developed framework that could scale well if you add up another machine, another machine, another machine. So this distributed setting. And there is no unique definition, but rather some like characteristics or properties for NoSQL databases. They should be horizontally scalable, so be easy to be utilized in a cluster environment, to be non-relational, to be distributed, which is all implicitly in this horizontal scalability, be schema-less. You no longer have specific header where you're being told or you're telling the system which column has which explicit data type, and it's open source, at least for most of the systems. There are also quite some proprietary ones. And most importantly, this once holy grail of relational database management systems is no more, it's gone. Instead, we have something called Base, an artificial concept for NoSQL databases, and it comprises basically available. So a system is generally available, but some data might not at any time due to node failures. I mean, because if you have several computers, the more computers you have, the higher the probability that one of them fails. Either it's hard drive, it's CPU, whatsoever. Then we have soft state, which means the system state changes over time, which means that stale data may expire if it's not refreshed. That you and you have this aspect of eventually consistency, which means the system is consistent from time to time, but not permanently, not always, and updates are propagated through the system if there's enough time. So this strong consistency, you have a consistent state of your database, you do your transactions, and you end up again in a consistent state. This is not, this cannot be guaranteed in this NoSQL realm. So base is placed on the opposite of acid, also from a chemical perspective. And when considering consistency availability spectrum, we shall see where it actually fits. So we have three aspects: consistency, availability, and partition tolerance, according to the Brewer's cap theorem. There are two types of consistency corresponding to a distribution setting. We have logical consistency, which corresponds to sharing, so the data is consistent within itself, data integrity. And we have the replication consistency, which means the data is consistent across multiple replicas, so on multiple machines. So the consequence from these different consistency levels that we have is the so-called cap theorem by Brewer. So any networked shared data system can have at most two of these three desired properties: consistency, availability, and partition tolerance. You can have either consistency and partition tolerance, consistency, availability, or availability, partition tolerance, but not all three of them at the same time. However, since we are pursuing also to get the most recent insights from science, this Brewer's cap theorem by Brewer himself has been stated that it can actually satisfy all three of them, given that we have sufficient redundancy in your hardware. So if you have put enough machines and enough network communication capabilities to it, then you are getting close to the situation where all three aspects are at the same time satisfied. And we have here this any partition system horizontally scaled, so having more and more computers connected together, needs to give up either perfect availability or perfect consistency. So it can't be consistent in the sense, for instance. So availability, as an example, each client can always read and write. Consistency, all clients always have the same view of the data. And there are like four, how to say, flavors of or main branches of NoSQL data models. And we shall have a quick look over them. The first one is the so-called key value store. This is like the most basic form of database systems. You store key value pairs similar to a dictionary or to a hash table and retrieve the values by accessing them by their keys. And the values can be of arbitrary format. So they can be files, they can be images, they can be scalars, whatever. And they are very heterogeneous systems. So you do not have all of them of the same time, of the same data type. So some systems, they support ordering of keys that permit an efficient querying, like range queries. Some other systems, they support in-memory data maintenance. Some use disks, and so on and so forth. And one of the prominent key value storage is, for instance, Redis or MongoDB from Humongous for being capable to capture massive amounts of data. That as a document store which relies on this key value architecture, we have here, as an example, MongoDB or CouchDB. They rely on XML or JSON or BSON binary JSON format. They have semi-structured data records that do not have a homogeneous structure. So columns, they can have more than one value. They can be actual arrays, in contrary to relational databases where a column consists of a single scalar value for each cell of a column. The documents include some internal structure, some metadata, data structures. They enable efficient use of indices. And we have wide column storages. So the rows are identified by keys, and the rows can have different number of columns, up to millions. And the order of rows, they depend on key values. Like locality is important, that those that are similar to each other are also on the same machine, on the same node. Then we have multiple rows can be summarized to families or tables, they call it, also among the literature, tablets. And we have multiple families that can be in turn be summarized to so-called key space. And the main focus in these wide column stores is availability. So they are used to ensure high availability. Example is Cassandra, that has been, I'm not sure if they still use it, has been used in Meta on the Facebook platform. Then we have graph databases. So they use graphs to store and represent relationship between entities. They're composed of nodes and edges. And each of the nodes and each edge can contain properties, like in graphs. So you have this graph-like properties. And you see here, like Alice knows Bob, Bob doesn't like Alice, okay, for whatever reasons. Alice knows Carol, and so on, or Dave lent money to Bob, and so on and so forth. And indeed, so I personally used graph databases in context of a project where we took lectures or modules, translated them into a graph structure, into a very simple mind map, actually, and we fed a Neo4j database with these mind maps. Why all this hustle? Because students can then see similarities or connections within modules or between modules. Excuse me. And here we have, at long last, this picture. You see different colors for the different types or flavors of NoSQL databases and where they can be roughly placed. So what we have here is, or take-home message, we have here 4 different types. And these different types are serving different edges of our CAP triangle from our CAP theorem that we have. So either serving consistency and partition tolerance, or consistency and availability, or availability and partition tolerance. And now coming to the last part, I have to ask Audrey, how much time? Or am I already overdue?
No, you still have about 15 minutes.
That's very good. Thank you. So we come here now to big data. But wait, didn't we say that NoSQL is already part of big data because relational database model did not scale up horizontally? Yes, but there is something more behind it. So let's say we have the drawbacks of the relational database management systems when facing large amounts of data, or massive amounts of data. So database systems are difficult to scale, at least horizontally. Database systems are difficult to configure and maintain. Well, that's debatable. We have a diversification available system. In available systems complicates its selection. And we have a peak provisioning that leads to unnecessary costs because they usually provide more resources than actually needed. On the contrary, we have the advantage of NoSQL systems like so-called elastic scaling. You have less administration, you have better economics, whatever this can be debated about, whatever better economics means. And we have flexible data models, meaning that we do not have this hard static schema as we have. However, NoSQL drops a lot of functionality from relational database management systems. So it's not everything gold that glitters. And we have as a concrete drawback, no real data dictionaries, but some sort of semi-structured models for providing the metadata. So you have issues or difficulties to access the data without actually knowing or having knowledge on the data model. Then you have transaction processing that is constrained by the CAP theorem, that you can't have consistency, availability, and partition tolerance at the same time. It's often limited access control, so we do not have this highly sophisticated transaction and access control as we have in relational realm. And we have limited indexing, so the efficiency is most replaced with scalability. Because SQL queries or relational database management queries, they are really massively optimized. But if we take all these things back that NoSQL is not serving, what do we end up with in the end? What is left? And well, we have the storage of massive amount of data in cluster environments through sharding and replication. Okay, we have some eventual consistency, and we have some database-like API, like Cypher query language from the graph-based query language. But what exactly are NoSQL databases then so much different from a classic file system? A classic file system on your laptops, on your computers with CSV files on them. Well, turns out to be not that much. And as a recap, there was something about the data science process that we had. So that involved pre-processing, and there was something about the data pyramid that, if you recall, you have a lot of data, and with every step, your data shrinks and shrinks and shrinks during this pre-processing step. And let's face it, the majority of analysis is still run on files. I have to admit, for myself, from my own side, I do a lot still on CSV files, which doesn't mean that you should forget or not use, or it's not useful what has been told before. This is also due to my own, how to say, laziness or taking things too lightly and recognizing after 3 weeks of work, oh, I should have used one of the relational database or a NoSQL database. However, machine learning, statistics, and data mining methods, they usually access all available data. So they do not have some selective access, but go over all of it. Most data mining and statistic methods, they require a well-defined input and not some semi-structured objects. That tells us that NoSQL approaches do not fit here. So we have, in the end, scalable data analytics that is happy or is already satisfied if we have plain files or CSV files or data in a distributed file system. So analytic methods can be parallelized on top of a distributed file system. So we use our CSV files, comma-separated value files, but not on a single machine, in a distributed fashion. And this is where we get into a realm of parallel computing, of cluster computing architectures. So we have computing nodes that are stored on racks, like typically 8 to 64 racks. The nodes on a single rack, they are, however, connected by a network, usually a gigabit Ethernet, through some sophisticated architectures like butterfly architecture or dragonfly network architectures to have a good balancing of communication overhead. And we have here switch, we have several racks. Within each rack, we have then our computing nodes stored. This is an image from Google's Mays County data center. And the characteristics of these so-called large-scale file systems is the files are several terabytes in size. So like Facebook's daily log as an example are 60 terabytes, or the 1000 Genomes project, 200 terabytes, Google Web Index, 10 petabytes and counting. We have here like files that are rarely updated, and it reads and appends are the operations that are most common. So if you're going to update files, which happens in business cases, or if you have some booking of flights or whatsoever, where things are changed, they are updated, then this may not be a good approach, or is not a good approach. But for analytics purposes, you have your data, this data is static, and you're going to analyze it afterwards. So in this case, you are going to have a lot of read and maybe just append operations, but not delete or update operations. And example for these large-scale file systems is the Google File System GFS, or Hadoop HDFS, or Cloud Store, or Amazon S3, and whatnot. What about the organization? Well, the files, they are divided into chunks. So you have your files, they are taken as one big cookie, and then or one big bar of chocolate, and then they are like split it into smaller chunks, typically 60 to 64 megabytes in size. Deviations are also possible depending on the use case. These chunks, they are replicated n times. As a default of HDFS, Hadoop data files system, n equals 3, meaning that at n different nodes, best case scenario, the replicas, they're located on different racks, on different nodes, on different racks for having a higher fault tolerance. So this replication is to have the situation where you do not have all the computation being burdened on a single node or on a small number of nodes, and to have, through this redundancy, also a huge safety against failures. Because if you have your data on different nodes, and these nodes are on different racks, if even the entire rack is broken, no problem, because the other replicas are on different racks located. And how to find or track these files? Well, there's a primary node which holds the meta file, a so-called directory, with information about the location of all the copies. So this is like the one who knows it all. And all the participating participants or participating nodes, the computing nodes, they are using this data file system, distributed file system, to know where the copies are. So they make a signal, or they ping the master node and say, hey, where is actually this particular file? And the primary node replies and says, hey, look, it's on this other node where you can take it. And we have this HDFS as a distributed file system that provides some high throughput access to the data. And it has, so refraining from this naming, it has a primary and a secondary, or a managing node and a computing node architecture, which looks like, that's quite some, looks complicated. What we have here, what is the take-home message? We have some name node, or the primary node, and we have here these computing nodes that are on different racks, and on these different racks, we also have this different replications of our data. And we have a client software, or script that we let running, and yeah. But let's oppose them, since we have, on the one hand, this MapReduce architecture, and then we have data handling, data management, and we have this relational database management systems. How do they differ? With respect to data size, MapReduce can operate on petabytes of data, where relational database management systems on gigabytes, or best case terabytes of data. Then we have like access. MapReduce accesses the data in batches, whereas relational database management systems can access them in batches or interactively directly. And regarding updates, we have in relational database management systems, what is possible, a role of read and write, and that quite frequently, Whereas contrary to that, we have in MapReduce realm write once, read many times paradigm. And the structure that we have here is a dynamic schema that may change, like different columns, different attributes, different data types, where we have a static schema in relational database management systems. The data integrity is low in MapReduce, and due to the normalized data is high. So we may face inconsistencies quite easily in the MapReduce scenario. However, what I know from some other colleagues, from a colleague in Tübingen, he said, no problem, you take your data, normalize it first in a relational database management system partially, and then feed it back, and then you have a high integrity maintained, at least for the snapshot. And the scaling, MapReduce scales linear and relational database management systems non-linear. So what happens if we now compare MapReduce not to relational, but to other high-performance HPC systems? Well, accessing this large data in volumes becomes a problem in HPC setting, as the network bandwidth is the true bottleneck. So it's no problem. You keep adding another computer, another computer, another computer. That's all fine. But the communication between these computers, that brings it down to its knees. And this is solved through data locality in MapReduce. So the data flow must be handled explicitly So this is solved, this bottleneck, by data locality in MapReduce. And the data flow, as a second point, data flow must be handled explicitly by programmers in HPC. I recall when I have learned to work with message passing interface, MPI or OpenMP, the different flavors, I had to explicitly state which memory is allocated, which node is changing data with which other node. And this is all abstracted away through this higher level programming by this MapReduce architecture. I mean, if you use something like PySpark or Spark and its Python implementation of it, you just keep writing code. Those of you, for instance, who use GPUs or GPU computing for their machine learning models, you just call in TensorFlow or in PyTorch your function calls, and all of that stuff behind the communication and whatnot and allocation of resources is abstracted away, actually. And the handling of partial failures depends on the HPC architecture, whereas MapReduce has a shared nothing architecture, so there's no dependence of tasks. And the only single point of failure is actually this primary node. If that one fails, then we have some trouble. But if all the other nodes fail, it's all fine. And well, in general, MapReduce can be used to manage these large-scale computations and have some failure tolerance with respect to hardware faults. The system mesh itself, as we stated previously, there's something called like heartbeat, where every of the computing nodes sends a heartbeat which contains information of how much resources are available, if the node is reachable at all or not, because the primary node pings, and if there's no response, then the primary node says, okay, this computing node is not intact, we can discard it, and reschedules the computation. And there are several implementation and flavors that exist here. And there's a zoo of different packages, so it's in its own ecosystem. However, like anything else, there are limitations to it. So it's a successful batch-oriented programming model, but if you have graph analysis, stream data processing, you need other tools. And there's a demand for growing real-time and ad hoc analysis. And there are some solutions in Hadoop and MapReduce. Yeah. And with this, I actually conclude. So the core message here is there are different flavors, different methods, different tools for data management, data handling. But as usual, it strongly depends on what your requirements are. And yeah, thank you for the time. And that concludes at this point the talk.